Hello, student. Welcome to the session 10 of this paper electricity and magnetism. So, uh, it is the continuation of the transient currents, and in this session, we are going to study the charging and discharging of the capacitor in an LCR circuit with the damped, undamped, and overdamped conditions. And these are the learning objectives. So we have to study the charging and discharging of the capacitor in a LCR series circuit with the damped, underdamped, and overdamped conditions to solve the problems based on charging and discharging of the capacitor in LCR circuit. Session outcomes: we'll study the charging and discharging of the capacitor in a LCR circuit with the damped, underdamped, and overdamped conditions. And also, we'll be able to solve the problems based on charging and discharging of the capacitor with different conditions. So now I am considering an LCR circuit. L stands for inductor, C stands for capacitor, and R stands for resistor. These three components are connected in a series across a battery. A battery is there, and here one key is there. All are in series. So consider the LCR series LCR circuit with the DC source with the EMF of E volt and having a key. When the key is closed, the capacitor getting charged at any instant. Let I be the current. Let VL, VC, and VR are the potential drops across inductor, capacitor, and resistor. So this VL, VC, VR. VL is the voltage drop across inductor. VC is the voltage drop across capacitor, and VR is the voltage drop across the resistor. And I is the current flowing through the circuit. Then we'll apply the current Kirchhoff's voltage law. We have E is equal to IR plus L into di by dt plus Q by C, where IR is the voltage drop across the resistor, and L into di by dt is the EMF or the voltage drop across the inductor, and Q by C is the voltage drop across the capacitor. Then same equation we can write in this way by writing I is equal to dq by dt. So because dq by dt is a current, so therefore I am replacing this I with the dq by dt. Equation 1 is written in this way: R into dq by dt plus L into d square q by dt square plus q by c. And rearrange the terms in this way, and the equation takes the form like this: d square q by dt square plus 2b into dq by dt plus k square q is equal to f. And here some constants are there. These are 2b is equal to r upon L, and 1 by LC is equal to k square, and E upon L is equal to f. These are the things we have to substitute here. This is equation 3. And the growth of the current in the LCR, in the growth of charge or current in the LCR circuit is given by this equation. It is the complete solution of equation 3. Q is equal to E raised to minus BT into the bracket A E raised to MT plus B E raised to minus MT plus Q naught, where M equals root of B square minus K square, and F by K square is equal to Q naught, which is the maximum charge on the capacitor. The value of A and B can be calculated from initial conditions. Therefore, initial conditions means I will think that when the key is open, the charge and the capacitor is zero, and when the key is closed, after some time the charge on the capacitor is maximum, like that. These are the initial conditions. So by applying these initial conditions, the constants a and b are obtained like this. So a is equal to minus q by q naught by 2 into the bracket 1 plus b by m, and b is equal to minus q naught by 2 into the bracket 1 minus b by m. So we have to substitute this a and b into the equation 4, and then we have to simplify the equation 4. It becomes q is equal to e to the power minus bt, and minus q naught by 2 is common. It is taken outside the bracket, into the bracket 1 plus b upon m into e raised to mt plus 1 minus b upon m into e raised to minus mt, the bracket completes, plus q naught. Substituting a and b. Substituting the values of b and m in the above equation. So b and m, b is equal to here b and m is equal to root of b square minus k square, but b is equal to r upon 2l. From this b is equal to r upon 2l, that we have to substitute. So substituting the values of b and m in the above expression, we are getting in this way. Wherever b is there, that is, for example, e raised to minus bt is there, this b is replaced with r upon 2l, and here b upon m is there, this b is replaced with r upon 2l, whereas m is replaced with the root of b square minus k square. So in this way, this equation is simplified. So this equation gives the value of charge in LCR circuit at any given instant of time. We will consider the special cases here. When b square is greater than q square, this root of b square minus k square is a positive value, so is a real one. This indicates that the charge on the capacitor gradually increases exponentially and also asymptotically to q naught. This is shown. This is shown by a dotted curve in figure 2. So figure 2 is here. This is the figure 2, and here dotted line is there. This dotted line represents the case 1. This one, this dotted line represents the case 1. So at this case, r square divided by 4l square is greater than 1 by LC. Next, we'll go to case 2. When b square is equal to k square, so this factor rule, square root of b square minus k square, becomes 0. Then the charge equation is reduced to this form. So q is equal to q naught into the bracket 1 minus e raised to minus rt upon 2l. It becomes. Under this condition, the charge and the capacitor increases exponentially and is shown in figure 2. So the curve for figure 2 is shown like this. Sorry. So this is case 2. A solid line is there. This is the case 2. Here also the charge and the capacitor increases exponentially like this, like case 1. Next, we'll move to the case 3. When b square is less than k square, r square divided by 4l square is less than 1 by LC, or square root of b square minus k square becomes imaginary because it is a negative value. Because b square is less than k square means the square root b square minus k square is a negative value, so the square root of a negative value is imaginary. That is the average. The charge on the capacitor is oscillatory, and it is damped as simple harmonic motion with the frequency omega is equal to root of k square minus b square. And the solution of this equation is under this condition is like this. Q is equal to Q naught into the bracket 1 minus e raised to minus bt into k divided by square root of k square minus b square into sine of omega t plus theta. So the charge equation becomes like this for the case 3. And this case 3 is shown here. This is the case 3. So in case of case 3, the charge and the capacitor becomes oscillatory. It becomes oscillating one. And these oscillations are not they are not the sinusoidal functions of time, because they are not, the amplitude is decreasing. The amplitude of these oscillations is decreasing, and hence these are called as damped oscillations. Whenever the amplitude of a wave is decreasing continuously, that wave is called as a damped wave, or the oscillations are called as the damped oscillations. So that is the case 3. So for the case 3, this is the frequency and the angular frequency, and the frequency of oscillation is given by f is equal to 1 by 4 pi root of 1 by LC minus 4 r square divided by L square, and tan theta is equal to square root of k square minus b square divided by b. This gives the phase of the um, phase angle. Then what is the limiting case here? In the limiting case, b is equal to k. When b is becomes equal to k, 1 upon LC becomes equal to r square upon 4l square. This implies that r is equal to 2 into root of LC. At this stage, the discharge is just about to become oscillatory. The circuit is said to be critically damped, and the resistance R is called as the critical damping resistance. That means when the resistance equal to this value, R is equal to 2 into root of L upon C is taken, uh, the discharge in the capacitor becomes oscillatory like this. It becomes just oscillatory. Means the oscillation just starts. So that is why this value of R is called as the critical resistance for the critically damped oscillations. So this is the limiting case. So now we will study the discharge of charge in the LCR circuit. Same circuit is there. We have to use another key here. Two keys are there, K1 and K2. When K1 is closed and K2 is open, this part of the circuit is closed and the capacitor starts charging. That means the charge on the capacitor increases. So after some time, what we have to do? We have to open the key 1 and we have to close the key 2. So when K2 is closed, this part of the circuit is completed and the charge on the capacitor starts decreasing through this inductor and resistor in this circuit. So we have to apply the Kirchhoff's voltage law to this part of the circuit. So we are getting 0 is equal to IR plus L into dL by dt plus Q by C. And substitute I is equal to dq by dt, and di by dt is equal to d square by dt square in the above equation. The above equation, this equation becomes like this. Wherever I is there, you replace that with the dq by dt, and like this. So rearrange the equation. Again, we are getting a differential equation here. It is actually a differential equation with these coefficients 2b is equal to r upon L and 1 by LC is equal to k square. So it is a differential equation and we have to solve this differential equation. The solution of the differential equation is given by this equation. Q is equal to A into e to the power minus b plus root of b square minus k square into t plus b into e to the power minus b minus root of b square minus k square into t. where A and B are the constants and can be determined from the initial conditions. The values of A and B are obtained as usual in the as in earlier case they are given by like this, and we have to substitute these values of E and B back into the equation 17. This equation 17, it is not equation 11, we have to substitute into equation 17, and equation 17 becomes like this. So this is the equation 17. Just substitute A and B here. Here A is there and here B is there, and simplify, you will get this equation 19. The above equation gives the value of charge on the capacitor at any time t during an LCR series circuit. During decay in an LCR series circuit. So next we'll move ahead. Here also three cases comes, and when b square is greater than k square, r square divided by 4 l square is greater than 1 by lc. The charge decreases rapidly with time. The discharge is known as aperiodic, deadbeat, or non-oscillatory, and is shown in figure 4. So in figure 4, this case 1 is there dotted line, that is the case 1. So it is not oscillatory, simply it is decreasing exponentially. That kind of line or curve is obtained for the case 1. Next, case 2, b square is equal to k square, and these two becomes equal, and this that square root term becomes 0, and the charge equation becomes q is equal to q naught e to the power minus b. This represents critically damped discharge, which is oscillatory or non-oscillatory, and is shown in figure 4. So this one, case 2, just to start the oscillation, just to start here. So that is why it is called as the critically damped case. Critically damped, just about the oscillation starts with the damping, case 2. So next, case 3 is there. Case 3 means when b square is less than k square, this quantity becomes less than 1 by lc into, and the charging equation becomes q is equal to q naught into k into e to the power minus bt upon omega into cos omega t minus theta. So this is the equation of damped oscillatory discharge, and is as shown in the figure. The amplitude of successive oscillations in the discharge decreases exponentially with time, and hence it is called as a damped oscillation. So case 3 is shown here. So in case 3, the conditions are such that the discharge of the charge in the capacitor becomes oscillatory like this. It becomes oscillatory, but the amplitude of these oscillations is continuously decreasing exponentially, and hence these are called as the damped oscillations. So damped oscillations are produced. So this is and hence the condition that the discharge of capacitor may be oscillatory. For this case I explained. Then the time period of the oscillations is given by this equation. F is equal to 1 by 2 pi root of 1 by LC minus r square by 4 L square. If this r is neglected, by assuming that it is very less as r its effect is very less as compared to L and C, then this equation becomes F is equal to 1 divided by 2 pi into root of LC. So using this equation, we can determine the frequency of oscillations in an LCR series circuit. So this is the theory. Now we can see some problems here. A capacitor discharges through an inductor of 0.1 Henry, and a resistor of 100 ohm is there. If the frequency of discharge is 1000 Hertz, calculate the capacitance. So capacitance is needed. This is the formula. So in this formula, you substitute everything. Everything is given except C. So you substitute and simplify for C, and C becomes equal to 0.252 microfarad. The condition for the charge on the capacitor increases exponentially and asymptotically to Q naught. So this is the case of B square greater than K square. The condition for the oscillation to start during charging in LCR circuit is B square is less than Q square. The condition for the charge on the capacitor increases exponentially in LCR circuit is B square is equal to Q square. The critical damping resistance in LCR charging circuit is given by R is equal to 2 into root of LC. Option E. Different options are there. R is equal to 2 into root of L by C is the correct answer. So E is the option. The condition for the charge on the capacitor decreases rapidly with the time during discharge in LCR circuit is B square greater than K square. So in the summary, uh, the expression for charging up the capacitor in LCR circuit is derived. Also, the different cases for damped, underdamped, and overdamped conditions during the charging of the capacitors are also studied. So these are the reference books. So go through them, and these are also available in our library. You can use them. Thank you for listening. Okay.